Welcome to springlib.
So let's begin by taking a real number in 0, 1 and write it in binary. So for instance, x, we can write it as 0.1011100011110 and so forth. Now we check in which position the ones are. So we have one here in the first position, we have one here in the third position, in the fourth position, in the 8th, and in the 9th, and in the 11th, and so forth. So let's define a set S of x as the set containing the position of every one in the binary expansion of x. So in this case it would be 1, 3, 4, 8, 9, 11, and so forth. And of course this is a subset of the set of positive integers. So let's define a function that goes from the power set of the positive integers to the interval 0, 1 that takes a set S to an x such that S of x is equal to the S that we're given. Or another way, if S, for instance, is given by 1, 2, 3, then x must be the number whose positive expansion has ones in the first, second, and third position. So now, is this function injective? Let's assume that f of the set A is equal to f of the set B. And of course, this is a number written in binary, let's say. Then we know that the integer I is in the set A if and only if, by definition of f, the ith digit of this number written in binary is a 1. But at the same time, because this number is also f of b, that means that I is in b as well. And this must be true for every I, well, for every integer I. That means that the set A and B contain exactly the same end elements, and therefore they're equal, which means that f is injective. Now for the surjectivity, we just observe that if you take x in 0, 1, you can just take the set S of x as defined up there in green, and by our definition of f of this set Sx is indeed equal to x, and therefore f is surjective as well, which means that we have a bijection between the power set of the positive integers to the set of real numbers between 0 and 1. So we've just shown that the cardinality of the power set of Z plus is equal to the cardinality of the interval 0, 1. But now we know that the cardinality of Z plus is strictly lower than the cardinality of the power set, and this was proven in exercise 35. And also we know that the cardinality of the interval 0, 1 is exactly the same as the cardinality of the set of real numbers. That was exercise 34. And therefore we've shown that R is uncountable.